here. Alright.
Alright, so let's start this over. It's in the wrong place. Okay, who can tell me what this is right here?
Parabola.
Right, but what is that architecture?
Oh, it's an arc.
It is a parabola. It's an arc. It's the St. Louis Arch, right?
Yeah.
So it's in St. Louis, Missouri.
If they were migrating from the east to the west,
Right.
that's like the thing about they passed through there.
Good. So actually, this was built in the 60s, but it denotes the gateway to the west. That's exactly what it denotes. Yeah. So looking at this parabola, I actually went to St. Louis this summer. I was speaking at an education conference, and I wanted to come in between the arch and lay down in the very middle. Because what would I see if I was laying down right in the very middle between the arches? What would I see? A straight line, right? Everybody can visualize that. If I'm laying down right here and it looks straight up, the arch is going right over. Right? Makes a line. Einstein talked about that, talking about perspective, making shapes and shapes and functions look differently based on your perspective. So he's saying, yeah, it's a parabola, but if you're right underneath it, it's flying over you, it's a line. So that kind of idea opened up again. Huge ideas about morphing different and translating different objects based on the perspective. So does anybody know this? There's an elevator that actually goes to the very top. Everybody know that? Okay. Yeah, it would kind of have to tilt. It's probably sideways. Or a swivel. All right, where do you think that elevator stops?
At the top.
Right at the top. Is everybody okay if I call this the maximum? Does everybody understand why that's the maximum? Okay. It's at the very top, it's the maximum. And then what would you say if I give my other laser?
Go.
So if I'm moving this line across, I want you to tell me where the arch is symmetric on both sides. Tell me when to stop.
The maximum.
Right there.
The maximum.
Does everybody agree that where that axis of symmetry, where it's symmetric on both sides, is the same or goes to the same point as the maximum?
Yeah.
Does that make sense?
Yeah.
Everybody? So we find the axis of symmetry where it's the same on both sides. So this distance between the axis and the arch on this side is the same as on this side. If I'm laying down on the bottom, the distance from the very bottom of the arch to the middle is the same as from the middle to the other side. Does that click? You see how it's a symmetric function, so we can see that. So we're going to look at that and some other objects here. The other thing about parabolas is anything you throw, baseball, anything, a bullet traveling, it's always going to make the shape of a parabola. Because gravity is constant, it's negative 9.8 meters per second on Earth. So any object that is propelled to the air will always follow this exact shape. That's also one of the reasons why they use it in architecture. So I look here and what do I see? This is a parabola.
Yep.
Eiffel Tower here in Paris. The reason they made it a parabola is because, like I said, all objects, if they're thrown, gravity interacts with them and creates that exact shape. So it turns out that the strongest shape that you can build with and distribute weight is also a parabola. It's also a parabola. I think that connection is kind of key. Isaac?
Oh, if you go right to the center of the Eiffel Tower and lay down on it, and I mean inside the Eiffel Tower, then
Sure.
you would see a square.
You would see a square, and the parabolas on each side would kind of be, looking like that,
Yeah, they would be like.
kind of tilted in. That's a good observation. Good perspective taking. All right, where's my maximum? Here, here,
Yes.
right there. Does that make sense?
Yes.
Where's my axis of symmetry?
Yes.
Here, here, right there. Ta-da! Is that pretty easy to find every time? It's always at the tallest point, and it's where the left and right totally match.
Yes.
Okay, just want to make sure. All right. So then, let's look at some other objects. All right, we know this bridge. The reason they made it a parabola is because that's the strongest shape that you can have. Gravity is already pulling down these cables in this exact shape, so they attach the other cables to it, and it makes it the strongest shape. So you can think of this too. This is like next level. If this, you understand this. If I have a roller coaster, right, that goes up and over, if it was a parabola, then gravity would act on that roller coaster car at the same exact shape as the parabola. But you've seen some roller coasters where it just kind of goes up. It does just a semicircle and then goes straight down. Okay. One thing to think about is when you're creating a roller coaster, since the natural path of an object is in a parabola, anytime you change or modify the parabola shape, it creates and exerts different stresses on you. So instead of being in a parabola shape, if you made it more of a oval or a semicircle, you're going to feel that difference. Okay? So that's just an idea of thinking about how they even design roller coasters.
Isaac. Oh yeah, and I'm guessing the line of symmetry is in the middle of the bridge.
Right. How about right here? It's kind of from a side perspective, so it's a little hard to see. But yeah, we have the line of symmetry here. And it's kind of at that degree where it's from an angle, you can't quite see it. All right, here's a water fountain. And I want you to think about this. Is this a nice looking fountain?
Yeah.
Is it nice? Yeah. Are these shapes, the shape of this, kind of familiar? You've seen fountains, they follow that kind of shape?
Yeah.
Okay. So I want you to think of this. Our qualities of aesthetics, of beauty, are also based on the parabola. Okay? So, not just because we've seen it all the time, but it's really that matter, water, whatever it is, interacts with our gravity in this exact way. So it's even connected to our sense of what is beautiful. If this was Jupiter, it'd have a different gravitational constant, more gravity. So it wouldn't go as high, maybe it would go, I don't know if it would even get out of this tube. But it would be much smaller and probably wouldn't go as far side to side. It would be like a very small parabola. So you can think of, on the moon, it would probably just keep going up as high as, actually I don't know how it would function on the moon, but it would definitely be higher. Gravity would not be as strong there. So the shape is also based on gravity. Okay, I'm going to keep going if that's okay, Isaac.
Yeah.
Okay, cool. So rainbow, parabola. Even light, as it goes through our atmosphere, creates a parabola. All right, here's some architecture as well. The stronger shape you can build, parabola. Okay, if you're shooting a ball, it makes a parabola, right? Where's the maximum? Right here, right? And if the ball didn't go into the net here, it would continue all the way down. You see how it would go down to here? Right? It would go all the way down if there's no net there. So here's an idea for you. If this is my line of symmetry, then the ball's path on this side would be exactly the same as the ball's path on that side. You agree with that? Okay. So if I set this up so that the ball would actually land way back here, right? And I found my line of symmetry. If I made a small hoop right at the very top, and that was where I'd throw the ball every single time, where it would go through that hoop and then start going down right away, all you'd have to do is throw it through that hoop right here, and it would go in the basket every single time. You see how that would happen? Because as I throw it, there's a maximum that's also my line of symmetry. The shape is going to look the same on both sides. So if I could just aim at a little hoop here, it would go through the hoop, and then I would know that it's going to go into the basket. Remember, the ball would usually go way down here. But because we have a basket, that's what we're aiming for. So it's just like another concept for you to think about. Yeah, William.
But wouldn't it matter how hard you threw it, though?
Right. So if there was a basket, here to throw it through, a hoop. If I threw it super hard and it just went through the basket and ended up going like that, right? So the thing is, at that hoop, that has to be the maximum. So right at that point, it also has to start going down right when it goes through that hoop. If you got that worked out, it would work. Okay. What are some variables that maybe would make this not work in the real world? Wind, backspin. When you throw their backspin in there. Okay, so those things are going to affect it. But if you can make it almost like a knuckleball, just kind of going through the air and it was in a vacuum tube, this would work every single time. It's close enough. The ball's pretty heavy. If it was not much wind, it probably would be close. Yeah. So let's see what else we have. All right, satellite dishes. Parabola, because the radio waves are, this is a radio wave satellite here, dish. So it comes in, it hits the parabola, it bounces up to the little receiver here. It comes down, bounces. No matter where it hits, bounces. The way the parabola is set up, if you have a dish on your roof, that little sensor there is gathering all the information that bounces off this. If you were up here holding on and there was a lot of sound out here, you would be able to hear it really well because every sound wave would be bouncing right at you. So this is how a satellite or a dish works. Another arch. Why did they make this arch a parabola?
Because it would increase the stability of the bridge.
Right? It matches how objects in gravity interact, so it creates that perfect path. The perfect path that's the strongest for bridges. All right, this guy, it's kind of hard to see the whiteboards, but it's going to the ski jump. What does he make? Parabola. So if you were a stunt worker, if you're a stunt driver, and you tried to do a launch, off of a ramp, you'd work all that math out first. You'd accommodate for all the forces. This is what you get in physics. We're learning how to be able to do that through this unit. Okay, so none of this stuff is, they have an intuitive feel of where they're going to go up and land. And even that is based on experiencing the parabola over and over and over. All right, here's the biggest dish there is, I think now. This is actually cut into a mountainside. It's in Puerto Rico. It's like a half a mile across. It's huge. And there's the receiver is actually dangling above it, so all the radio waves bounce off this and go right into the receiver. All right, we can't quite see it here, but a way to draw a parabola is if you make dots like so, and a y-axis and x. You connect x is 1, up here to y is 10. You connect x is 2 to y is 9. X is 3 to y is 8. And you do that, you're going to end up with this parabola shape. Can you kind of see the dots? Right here. Let's see if I zoom it in. So basically, you kind of see it now. So there's lines here. It's not as easy to see on this projector, but you can create a parabola also by that little trick. All right. So let's